I'm the runner-up.
Someone doesn't want to speak on
yes,
what?
Yes, the speakers are Mallory Bibler.
Yes, I know.
Gianna Justice.
And so if one of
if
them
one of them
freaks
doesn't
out
show up or just doesn't want to do it,
or freaks out, stage fright. What are you going to talk about?
It's either their speech or the speech that's handed to them.
Nice. All right.
Thank you. I appreciate that.
I will listen intently for you.
What kind of tea do you drink?
Huh?
What kind of tea do you drink?
That's just straight up regular black tea. Okay, conditional probability. No more digression.
Wait, I got one more thing to ask.
No, compound probabilities were when we had two different events and they had, like, if they were exclusive or if they were dependent or if they overlapped, because then if they overlapped and we counted them twice, you took them out. Conditional probability is similar to that, but it has to do more with you're given that it's already occurred. Okay, so the definition is the probability and events will occur given that an event has already occurred. Okay, so it's like you're having two compound events, but the difference is that we already know the outcome of one of the events. Okay, does that kind of make sense?
Yeah.
All right, so if it's an independent, then it's independent when the event that has already occurred does not what? What do you think if they're independent?
Does not occur.
Does not affect, but yes, the probability of the new event. Okay, so let's say I have a dice and I want the probability, and here's the formula. This little line right here means given. So it's if A is rolling a 6 and B is rolling a 1. Okay? That means that I would be looking for the probability of A rolling the 6 given that I've already rolled a 1. Okay? Now, since I already know this has occurred, do we even care what the probability has? No, because it's already occurred. So I'm just going to look at the regular probability for the very first one. Does that make sense? Okay? And just like, what's the probability of me rolling a 1 given I've already rolled a 6? Well, who cares if I rolled a 6 or not? It doesn't really matter. It's what's the probability of the B. Okay? Does that make sense? Kind of? When we get to the examples, you're going to go, oh, well, that's kind of, it's just basically the same. But, all right, it's when it's dependent, that's when the event has already occurred. Does affect the probability of the new. Okay? Now, that's kind of, and we'll get into those more when we get on the back examples, okay? But basically, what your formula is, what does it mean when it's A intersection of A and B? What does that mean in the big scheme of things? Is it everything in A? It's in A and B. Okay? So this is it'd be the items in both and are on the top, and the items second in the bottom. And when I mean second, I have A given B, so B goes on the bottom. Okay? Does that kind of make sense? All right, independent events. The event has already occurred. Oh, my spelling's horrible up there. And doesn't affect the probability. So really, all I'm looking for is the probability of the A. So what's the probability of a red cube and a white cube numbered 1 to 6, both landing on 3? If you know the white cube already landed on 3. If it already landed on it, then it's just that one single event, which is 1 over 6.
Even is like subtraction, correct?
All right, so what's the probability of both cubes landing on odd numbers if you know the white cube landed on a 3? Well, if it already did, it doesn't really matter. We just want to know what's the probability of it landing on an odd number the second time around. How many odd numbers are on a cube?
3.
So 3, 6, or 1/2. Okay? What's the probability of a penny, a dime, and a quarter all landing on tails if you know that the quarter, and we're going to change this back to dime because that's a little typo, landed on tails? So this time I have 3 events. Okay? I have the penny, I have the dime, and I have the quarter. Okay? So each of them are 1/2, 1/2, and 1/2. Do you agree with that one?
Yes.
Okay. I know that the dime and the quarter already did. So those probability goes away, which is what leaves me with just the penny. Okay? However, if I want to know what the probability is, if all I know is the quarter, well, my penny was 1/2, my dime was 1/2, the quarter was 1/2, but I only know this one. Now I need to multiply those two together. Good?
Yeah.
Makes sense?
Yeah.
Good? All right. Then let's do a table. Tables are real great and easy. They break it down really well. Okay, so they were surveyed about whether they were for or against or had no opinion about a proposal to increase funding for the school's football program. Okay, so we had 100 people total. What's the probability that a randomly selected student would be for the proposal given the student was a girl? Okay, so that means it would be the probability of 4 given she's a girl. Okay, now this is one that's going to be dependent. Okay, so that means that I would need the number of both. So 4 and girls over the number of girls. Would you agree with that? That's what the formula said. Well, if there are 4 and girls, that was 10. And my total number of girls was 45. Okay? And then simplified, that was down to, that's like 22%. Good? Make sense? Okay, now we're going to look at the probability it would be a boy given it was 4th proposal. So my top is both. So you're a boy 4. That was 40. And now I need the total 4, which is 50. Now, if you can't remember, think of it, if you turn your paper, there's your fraction. It's got to be the boys and the girls, or I mean the 2 categories on the top, and then the second category is on the bottom. Okay? All right, so we got a randomly selected student, no opinion, given the boy was a student. So, probability, no opinion, and a boy. So, my boys who didn't have any opinion were 10. And my second, given it was a boy, is 55. Which is going to be like 18.2%. Okay? Easy peasy? Sure. Yes? Are you saying that to be facetious? Or does this make sense? Whoever said that. Ooh, look at that. Everybody pointed. All right, good. All right, let's look at our Venn diagram. Okay, A is my 10th graders. B is the number of high school students that have a computer. Okay, I want to find the probability of A given B. Okay, I want to go down to number 9 first though. Okay, what does it represent in the context of the problem? Okay, so it's the probability. What's A represent? Student is a 10th grader. And then my little line is given. And then B is that they have a computer. Computer. Okay? Good? All right, so the probability of A given B, how many would be the intersection of A and B? 15, because it would be the A intersection B would be this portion right here, right?
Yes.
Okay, so that gives me 15. And then how many are in B?
45. 45. 10.
No, 10 are in both.
45. No, wait. I talked with my tongue.
Let's think. What's B?
90. It's 90.
60.
B is 15 and 45.
I'm about to drop this.
So
class.
that would give you 60. Does that make sense to you guys?
No, it does not make sense.
Why does it not make
Because how
sense?
come it has to be all of them together in a big
Say that
circle?
one more time.
Why does it have to be all of them together in a big circle?
Because that's all of the kids in B.
That makes sense now.
Okay. All right. Find the probability of B given A. Well, what's the intersection of B and U? we're still at 15, but now how many are in A? How many are in A? 35. Okay. All right. How do we feel about these? Questions? Comments? Concerns? You got like 15 minutes and there's, what, a whole 14? You should be able to get these all done before.
This whole packet?
14 questions, dude.
No way.
14 questions.
I don't think I'm gonna be able